I'm going to show you more examples, how we can allocate an array on the stack, okay, and more examples about bubble sort and recursion. Okay, so this will be my last slides in this presentation. I'm going to also post today, inshallah, I'm going to post the MIPS programming assignment number 2 will also be posted on Blackboard. Okay, so we'll have a second programming assignment on MIPS. Right, let me start here by showing how we can allocate an array on the stack. Now, in some programming languages, we can allocate an array on the stack. This will be more efficient than allocating the array on the heap. Remember that allocating an array on the heap will require a system call. Okay, so you have to make a system call and you have to manage the heap. Okay, but allocating an array on the stack can be done efficiently, because once you call the function can allocate a stack frame for itself, and it can allocate the space on the stack frame for if you have a local array or whatever are the variables or data structure that you have inside the function, they can be allocated in the stack frame. And once you return from the function, then this space will be deallocated, or it will be freed, okay, just before returning from the function. So in this example, I'm writing a function which is called foo. Now this function has a parameter which is n. Okay, so this is my only parameter, n. Okay, so this n must be passed in A0, register A0. Now notice that there is an array inside this function. It's a local array, and it consists of n integers. So n elements, these elements are of type integer. Now, once we have allocated this array can be allocated on the stack, as I mentioned. So it will exist only when we call the function, and it will be freed when we return from this function. So its lifetime is the lifetime of this function. Only when we call the function, it will exist. And then we can use this array. For example, I can call the function random to generate a random array. So the values can be generated randomly inside the array. And we would like to generate n elements. So we pass the address of the array in register A0, and we press the number of elements that we would like to generate in register A1. So we have 2 arguments, okay, for this function random. And then after that, we can call the function a print array. Okay, so this function a print. Okay, we pass again 2 arguments, array and n. We can do many things inside this function. Okay, and once we are done with the execution of this function, this function has to return back to its caller. So once we reach this closing curly bracket, we have to return back to the caller. So the function has to free the stack frame. Now, on top, we have the stack frame of the parent. So this is the stack frame of the parent function that is going to call the function foo. Notice that the stack pointer is pointing at the top of the stack frame. It's pointing at the top of the parent stack frame. And then once we call the function foo is going to allocate its own stack frame. Now, inside the stack frame, we have to allocate the array. Now, the array consists of n integers. Notice that the elements are of type integer. So we have to multiply n by 4 bytes. This is the number of bytes that we should allocate for the array. And then we have to save certain registers. Now, notice that we have some function calls here. We are calling the function random, we are calling the function print, and these 2 functions must, they might these two functions might modify the argument registers A0 and A1. And for this reason, we need to save, okay, these two argument registers, okay, on the stack. As a minimum, we need to save n, okay, but also we can also take care of the array. So in this case, n itself is my argument, A0. So as a minimum, we should save A0, okay, on this stack. In the case of okay, the array itself, we know its address inside the stack frame because the array is going to start at the beginning of the stack frame. In fact, since the stack frame is upside down, notice that this is basically the address of my array. So my array consists of n multiplied by 4 bytes, but we know where it starts inside the stack frame, and we can address it inside the stack. We need to save the return address. Okay, why? Because the function is a non-leaf function. And also we need to save the parent stack pointer. I'm saving it so that, okay, once we are done, we can just restore the value of the stack pointer so that it points back to the frame of the parent function. Okay, so yes, talk.
The last thing you said we must save the parent register. Is it?
Yeah, we're going to save registers here. So 3 registers in total. So what you have to do is that you have to see what this function is doing. Okay, so in this example, this function is calling 2 functions. It's calling the function random and it's calling the function print. So we must save n. And here is the argument for the function foo. So this is why we saved A0. We must save RA, which is the return address, because the function is going to make a call to the functions random and print, and therefore it's going to change the value of the return address. So we must save the return address for the function foo, so that foo does not lose its own return address. And finally, here I'm saving the stack pointer so that we can restore the value of the stack pointer just before we return back to the caller of the function foo, okay, the function that called the function foo. Now notice that once we make the call to the function random or the function print, they might have also frames for these functions, and these frames will be the frames of the child functions. So these are the functions that are going to be called by the function foo. Now, if the function random or print call other functions, they might actually have like nested calls. We'll have stack frames below the stack frame of the function foo. So the stack can grow dynamically at runtime. And once we start returning from these functions, then each function will free its own stack frame. That's really the idea, okay, of allocating and freeing stack frames. It's all about supporting functions. Fine. So if I would like now to translate this function foo, all this function is doing is calling 2 functions, the function random and the function print. But first it has to allocate its own stack frame. It has to allocate space for the array, okay, within its stack frame. It has to save 3 registers on the stack. So this is the translation of the function foo. Now, the first thing I need to do, I need to allocate the stack frame. Now, notice that my parameter here is n. And my stack frame here, the size of my stack frame depends on this parameter n. Okay. So unlike the previous examples in which we only saved a few registers, and we know the size of each register is 4 bytes, so we know exactly how many bytes we need to allocate in the stack frame. In this example, we don't know how many bytes to allocate in the stack frame because the stack frame depends on the parameter n, so it can vary in size. Okay, that's actually what makes this example different from the previous examples that we have seen in the previous lecture. Okay, so in this example, what we need to do is that we need to compute how many bytes we need to allocate in the stack frame. So I have A0. A0 here is my parameter n. Of course, the caller must pass n in the register A0 before calling the function foo. So the function foo expects, okay, this parameter to be in register A0. So the function foo, at the beginning of the function foo, we must allocate the stack frame. So first we are going to allocate this, we are going to compute the size of the stack frame. So here shift left logical is going to multiply the value of A0 by 4. We are shifting it by 2 bits. So this is multiplication by 4. We place the result in T0. And then we add to T0. We add the constant at 12. So I'm using add immediate. Okay, and we place the result again in T0. Now notice that T0 is a temporary register, so any function can modify a temporary register. Okay, so without the need to preserve its value on the stack. Now, so we have calculated here T0, which is n multiplied by 4 plus 12 bytes. The reason why we are adding 12, as indicated in the previous slide, is that we need to save additional registers. So these 3 additional registers here are going to occupy 12 bytes on the stack. So this is why I added 12. If you want to save more registers, then you just have to count how many and calculate the number of bytes. So now we know that the size of the stack frame is computed in T0. Now I would like to preserve SP. Now I need to allocate the stack frame. Now, in order to allocate the stack frame, notice that we have to modify the value of SP. This is the old SP, which is pointing at the top of the parent stack frame. And this is the SP of the function foo. Okay, so we have to adjust the stack pointer. Now, in order to adjust the stack pointer, we don't really want to lose the old stack pointer. So I really would like to save, okay, the parent stack pointer. Notice that I'm actually saving it in memory in this example. I'm saving the parent stack pointer. So what I'm going to do, I'm going to just copy the value of the stack pointer. This will be the old stack pointer. This is the parent stack pointer. I'm going to copy it into T1 and then allocate the stack frame. So to allocate the stack frame, I'm going to adjust. This will be the new value of the stack frame. So we subtract SP becomes SP minus T0, and T0 will be the number of bytes that we would like to allocate for the frame of the function foo. Now, once we have done this, I can use 3 store instructions here. I'm going to use here, okay, these 3 store instructions to save 3 things. I'm going to save the stack pointer. Okay, so now T1 here is the value of the stack pointer. This is the parent stack pointer. I'm going to save RA and I'm going to save A0. Notice that the displacement is different. I'm using the new stack pointer for the function foo, but notice that the displacement here is 0 plus SP. This is 4 plus SP, and this is 8 plus SP. So I'm using displacement addressing to store the values of these 3 registers, as shown here in this slide. So this is now the new stack pointer. Okay, it's shown here. This is the stack pointer, okay, for the frame of the function foo. So at 0 plus SP, I would like to save the parent SP. So to be the value of this pointer here. This is the old value of the stack pointer. And I'm going to save the return address. And I'm going at 4 plus SP. And at 8 plus SP, so we just add 8 plus the value of SP, and we save the argument A0. Because this argument is going to be modified. Okay, and we need to preserve the value of this argument because we are making function calls here. And we need the value of this argument. Right. So we have saved, okay, these registers, okay, using these 3 store word instructions. So the store is going to write memory, is going to write the stack frame. of the function foo. So we have saved them. Now what we need to do is that we need to make these two function calls. So I need to call the function random, and then I need to call the function print. So it is just a matter of making function calls, and then we are done. So in order to make the first function call, I'm going to copy. So notice that A0, I'm going to copy it into A1. And the reason why I would like to copy it into A1, because notice that the parameter n should be passed here in A1, okay, not in A0. It was received in A0 in the function foo, but I have to pass it in A1 to the function random. Okay, so this is why I have to copy it into A1. Now, I also need the address of the array. I need the address of the array, and the address of the array is at SP plus 12 bytes. So we know exactly where is the array located. Okay, so this array exists in memory on the stack. Okay, it exists on the stack. So we can locate it. Okay, we can simply compute its address, the address of the array. So I'm going to add here to the stack pointer, I'm going to add here 12 bytes, and I'm going to write the result into A0. So the result here will be the address. So now A0 contains the address of my array A. Okay, so this array does not exist in the static data segment. It exists on the stack. So we just allocated this array inside the function foo. And then I will make the first function call. So this is jump and link to random. We'll make the first function call. Notice that jump and link is going to modify the return address for the function random. This is why we save the return address of the function foo. Okay. Now, once we return from the first function call, okay, we are going to return. So this function random is going to return back to the function foo. So once it returns back to the function foo, we come to this instruction here. Now, this instruction is going to, okay, we need to pass again A0 and A1. Okay, A0 and A1, we need to pass the parameters here. Okay, so I need to pass the address of the array, and I need to pass n. Okay, so the address of the array will be in A0 and n will be in A1. So what we need to do is that recalculate SP plus 12 and then pass it in A0, because A0 might, okay, could have been modified by the function random. So we have to recompute A0, okay, which is the address of the array. Again, SP plus 12. That will be A0. And then A1, we just have to load it, okay, from memory, because we have preserved the value of n. So we have preserved it actually here. Okay, so we have saved n at 8 plus SP. So we load it. So we use here load word to load the value, to restore the value of n from the stack frame. So once we have the parameters, now we can make the second call to the function print. So now we have made a second call to the function print, and the function print will do its work. And then once the function print has finished the execution, it's going to return back here. It's going to return back to the function foo. So what we need to do is that we need to restore the return address. Notice that we have saved the return address using this store instruction. Okay, we save the value of the return address at 4SP. So we have to restore it. So we have to restore the return address of the function foo. We also have to load the old value of the stack pointer. That will be the stack pointer. So this load instruction is going to restore the parent SP, because we saved it, okay, on the stack. So once we have modified SP, so now SP is pointing at the parent function as shown here. This is the old SP, which is shown here again. We have freed the stack frame of the function foo. So this is the last step, is that we free the stack frame by restoring the old value of SP, and then finally we jump register to RA to return back to the caller of the function. So we return back to the caller, and we have restored SP to point at the frame of the parent function that called the function foo. Okay, so you can see that, okay, how things are translated and how we can allocate an array on
Dictor, why we add just 12 to register SP before we call random?
Because
Why we
see
don't?
that if you would like to find where is the address of this array, so this array occupies n multiplied by 4 bytes. N can be any number. It's an argument. Okay.
Okay.
So you can actually have a very large array here in memory on the stack. Okay, in the stack frame of the function pool. And you can allocate it as say 100 elements, 1,000 elements, whatever number of elements that you need. And this is the address. So basically, the array starts here at this address. Okay. So this is the address here of the array. So this is the base address. That will be the address of the first element inside the array. This is the stack pointer. So we can locate the array with respect to the stack pointer. Now notice that we have 12 bytes here between, because we have saved 3 registers here, 3. So these are 12 bytes. So we add SP plus 12. Okay, let me use my pen tool. I'm using my pen tool. Let me just use my pen. So this will be really, if I would like to look at the address here, it will be SP plus 12 bytes. Okay, that address, maybe it's not clean. That's the best I can do. I can do better, but, probably. I can just, let me re-erase it. Just, okay.
Just a small question, Doctor.
Yeah,
shouldn't
so
be the array from the beginning, I mean, from the top of the, you said the address of array will start from, if we just add
here.
12, right?
Yeah, but you see that the stack grows downwards toward the lower memory addresses. So this is the end of the array. So here, this is the end of the array. This is the beginning of the array.
Okay.
So this is where the array starts. Okay, on top, this is where it ends. Because when you would like to index the array, you would like to go up. Okay, not down. Okay, so you would like to start at index 0, then index 1, and so on. Is this clear?
Yeah, I just being confused why we start.
So you see that the array is upside down.
Yeah.
That's why. Good question. Okay, do you have other questions?
If you can just back to the.
Yeah. So we see that every time we add SP plus 12, we place the result in A0. A0 will contain the address of the array. Now, remember that this array exists on the stack. And it is relative to the address of the stack pointer. So this is why we always add the stack pointer to plus 12.
Victor? Isn't it better to save only the address in the stack pointer instead of the entire array?
Is it better to save the, sorry, again?
To save the base address of the array instead of the entire array on the stack.
And where do we have the array?
The memory. Okay.
Which part of memory?
Okay.
You see, you are not programming in a high-level programming language here, right? We are programming in assembly. So if you are programming in assembly, see that the compiler does all of these things for you when you are programming in a high-level programming language. If you are programming in C or in Java or whatever programming language that you are choosing, the compiler writer has to figure out where to place these things. You don't really worry about these things when you are programming in high level, right? Do you worry about these details?
No.
Okay, but this shows you that actually other people have done the work for you. Yeah, they have simplified programming for you because this array has to be somewhere in memory, right? This array has to be allocated somewhere in memory. So you have a choice. You can allocate the array on the heap. That will be one choice, and only use a pointer, okay, on the in the stack frame. Yes, you can do it differently. by allocating the array on the heap, you can allocate n multiplied by 4 bytes, and you can use a system call to allocate the array on the heap and use the address and save the address of the array in the stack. That will be one choice. And you will only have a pointer to the array, which is the address of the array on the stack. And then once you return from the function, you have to free the array that exists on the heap. You have to make another system call to free the array that exists on the heap. But to avoid these system calls, because these system calls actually might be expensive because the heap itself, okay, has to be managed, okay, and therefore you have to keep track of what has been allocated and what has been freed. But since here we are allocating in last in, first out, we are using a stack for that purpose, it will be a lot easier to allocate the array on the stack, because once we return from the function foo, this array will no longer exist. So it will make the code to be much more efficient. This allocation is a lot more efficient than allocating the array on the heap. So we can have the array as part of the stack frame.
Thank you. So if we want to use that,
for example, to some programming languages, how they are implemented, and if you really would like to understand how these programming languages are implemented, you will see a big discussion about how to allocate these objects, these arrays and data structures and so on. Okay, do we allocate them on the stack? We allocate them on the heap? It depends on how you are using them and their lifetime. Now, if this array, okay, has to still exist even after returning from the function foo, then it has to be allocated on the heap. In other words, if I need this array by the parent function, so then in this case, the function foo is going to allocate it on the heap, not on the stack, and returns its address back to the parent if the parent needs this array. So if the lifetime of the array, so if the array has to continue to exist even after returning from the function foo, we cannot allocate on the stack, we have to allocate on the heap. But since this function, since the array only exists inside the function foo, and it will cease to exist after returning from the function foo, it will be more efficient to allocate it on the stack. Okay, is this clear?
Okay, thank you. Very clear.
Yeah, okay.
Doctor?
Yes, تفضل.
Just to make sure I understood, where is array of index 0, where it will be its location?
So the first element in the array, so let me just go back to my pen tool here. So the array consists of n elements. I'm getting all of these emails. Okay, so the first element of the array will exist here. That will be at index 0. So this will be, let us say, array 0. This will be the value of the array. Then this will be at index 1. And this will be the last element at index n-1. Okay? So you can index it this. The normal way that you index an array. All right? طيب. So remember that you just allocate the array as part of the entire stack frame, and then you can index it. طيب. So these are the remarks on the function foo. I just explained how it works. So I'm going to skip the slide. You can read these remarks. I have another example which is about bubble sort. Okay, so now if you look at this bubble sort function, it's a leaf function. It does not really call any other function. So therefore, it might do all its work, okay, by using registers. Now notice that the array itself now here in this example, this array does not exist on the stack. This array exists elsewhere in memory, and we only get the address of the array. So the address of the array is passed in A0, and N here is the number of elements in the array. Now notice that the array, the function is written as a nested loop. We have here a do while loop, and inside I have a for loop. So what I really have to do is that I have to write a function that I have to write this function in assembly language. It has two nested loops, and inside the inner loop, inside the inner for loop, we have to load the value of AI from memory. I have to load the value of AI plus 1. I have to compare them, and if this is true, we have to swap. And then we continue swapping. If we are not, if nothing is swapped, it means that all the elements are sorted. So while swapped, it means that while swapped is equal to 1. While swap is equal to true. So notice that initially we initialize swap to 0 to indicate that nothing has been swapped by the inner loop. But then we enter the inner loop. If something was swapped, we have to repeat the outer loop, the do while. So we have to go through multiple passes. Okay. And every time we go through another pass, we decrement the value of n by 1. So really the complexity, this is an algorithm, okay, which is written in a high-level programming language. You can, of course, translate this function into assembly. The complexity of this function is big O of n squared because we are writing nested loops. Notice that after, okay, the first pass of the do while loop, I will guarantee that the largest element will exist as the last element inside the array. And then we can decrement the number of elements by 1, and then we can sort, okay, n minus 1 elements, and then the second largest would be okay, at index at the end of the subarray, okay, at index n minus 2, then n minus. So we go backwards and we start sorting, okay, the elements of the array. This is how bubble sort works. This is the algorithm for bubble sort. It's very well known, okay, algorithm. So the algorithm is given to us. I'm just copying it, okay, from another textbook. So I just got this function. I would like to take it as is and translate it as if I were the compiler. Of course, compilers do all of these things automatically for us. So the compiler writer has written the software that does the translation for us. Okay, that's actually how, okay, amazing compilers are, because they do this kind of translations automatically. Okay. Now the best case performance is big O of n. So the worst case is big O of n squared. Okay, so because you have to repeat the outer loop, you see that you have to repeat it n minus 1 times, and every time you repeat, you have to repeat the inner loop, okay, for that number of iterations. So basically you get 1 plus 2 plus 3 plus all the way to n minus 1. That's the number of the number of times that you are executing, okay, the inner for loop. And okay, so the first time you are going to decrement n by 1, so this is going to be n minus 1 times, then you have n minus 2, then n minus 3, and so on. So basically, if you add them backwards, it's the same thing as adding from 1 plus 2 plus 3 plus all the way to n minus 1. And if you would like to compute how many times you are executing, okay, the inner if statement and the swapping, you will find that you are doing it big O of n squared. Notice that in the swapping, we are loading the value of A of I, AI plus 1, and then I'm going to store the value of A of I and A of I plus 1, but I'm going to swap their values. And I'm going to indicate that they are swapped. Okay, so this is my function, and I would like to translate it into assembly. Now, there is a best case performance if the array is initially sorted. Okay, so if the array is initially sorted, then notice that when we enter, okay, the for loop, the if statement will never be executed, okay, because we'll never have A of I greater than A of I plus 1. It means that all the elements of the array are sorted from the smallest to the largest, and therefore we never execute the if statement, we never actually swap, and therefore just after going through one pass, only one pass, okay, through the do while loop, okay, then we terminate the do while loop, and therefore the best case performance will be big O of n. So we go through one pass of the array, and therefore it is big O of n, where n is the number of elements inside the array. Okay. Let me show you the translation of the function bubble sort. Now notice that I'm writing here a do while loop. So this is actually where do starts. This is where starts the function bubble sort. This is do. Okay, this is the end of the do. Okay, so this is here we branch. If it's not equal to 0, back to do. Just here. Turn off my camera. So notice that A0 is the address of the array. This is A0. And A1 is n, which is the number of elements in the array. Of course, the function bubble sort expects these two arguments in A0 and A1. Now, the first thing it does, as indicates here, that when we enter the do while loop, it says that n is equal to n minus 1. So therefore, it is free to modify its own argument A1. So A1 is n. So this add immediate is going to decrement the value of n. So this is the first instruction which is done inside the do while loop. So notice that do while starts here at do and then it ends at this branch not equal 0. Now, why branch not equal to 0? This is the while. Okay, it says that while swapped. So it means that while swapped is equal to 1, we loop back. Okay, so we check this condition at the end. So if it is not swapped, so here we say that branch, okay, while swapped is equal to 1. So we branch if it's not equal to 0. Notice that swapped here, I'm using register T1 to indicate that swapped. I'm using it here. So load immediate T1, 0. That's actually for swapped. So I'm initializing it to 0. Okay, but if it becomes 1, we loop back. If it remains 0 in the inner for loop, we do not loop back and we are done. So we come here to the jump register and we return back to the caller. Now that's okay for the outer loop. For the inner loop, it starts here at the 4 and it ends here at the branch not equal. So notice that here, how these loops are nested. Okay. Okay, so let's understand this code. Notice that we start always here at index I equal to 0. Index I here, I'm using T2 for I. So load immediate to 0. That's actually for the index I. I need to load the value of A of I and the value of AI plus 1. So I need to load them. Now, in order to calculate the address of A of I and A of I plus 1, I need this register T0. So T0 is nothing but the address of the array A. So we always start at A of 0 because the index I starts at 0. So we start always at A0. So this is why we have to initialize T0 to become A0, which is the address of the array A. And I need two load instructions. So load word and load word to load the value of A of I and AI plus 1 into T3 and T4. So now T3 and T4 will contain the value of A of I and AI plus 1. Notice that the plus 1 here, we use here for T0, because this is an array of integers. Okay? It's an array of words, and each word will occupy 4 bytes in memory. So once we have loaded the value of A of I and AI plus 1, it says that if AI is greater than AI plus 1. So notice that we have to load the value of AI and AI plus 1 into 2 registers before I can compare them. Okay. Now, if it is greater than, we execute the body of the if statement. If it is less than or equal, then nothing needs to be done, right? So I'm going to say here branch less than or equal to skip the body of the if statement. So this is the body of the if statement. So if T3 is less than or equal to T4, skip the if statement and go to L1. Now, when we go to L1, I'm going to increment I plus plus. Okay, so that's actually T2 becomes T2 plus 1. And I'm going to change the value of T0. So remember that T0 is used as a pointer, okay, which is the address of the next element in the array A. So every time we finish one iteration, I increment T0 by 4 to point to the next element inside the array. So T0 is nothing but the address of A of I. Notice that T0 is initialized here on top. at the address of the array. And then every iteration inside the for loop, we increment this address by 4. So we have to advance the address so that we can point to the next element inside the array. Now, notice that here I'm going to branch in the inner loop if T2 is nothing but I, the index I, that's T2. So we branch if T2 is not equal to A1, which is equal to N. Okay? So if it's not equal, we branch to the inner loop, back here to the for loop. So this branch here is for this for loop, and this branch is for the outer do loop. Okay? So this is actually where we branch. This is where we branch, okay? Right. So inside the inside the if statement, what I really need to do is that if I found that AI is greater than AI plus 1, I have to swap. And I have to indicate that swap becomes equal to 1. So to swap, I need two store instructions. I already have loaded the value of AI and AI plus 1, so there is no need to load them because I loaded them here before comparing their values. I only need to store AI and AI plus 1. So you see, you don't really have to follow this the way it's written in high level, because you see that already we have loaded AI and AI plus 1 before comparing their values. So why load again inside the if statement? I just need to store, that's it. So I have these two store instructions that's going to store T4 and T3. Notice that T4 is the value of AI plus 1, so I'm going to store it at the address of AI, so at 0 plus T0. Notice the store word instructions. So these stores are going to write, the values inside the array in memory. And this is going to store the value of T3, which is A. So T3 will be the value of AI. We're going to store it at the address of AI plus 1 at 4 plus T0. Okay, so by doing this, we have swapped the two elements in memory. Now I'm going to here to initialize T1 to 1. So T1 here is swapped. Notice that T1 was 0 before we entered the for loop. Okay, that was the value of T1. That's actually swapped. Now we make it so it was 0 before we entered the for loop. If we swap, we have to make it 1. So once we are done with the inner for loop, we come here to this branch not equal. If T1 is equal to is different from 0, it's not equal to 0, then we branch back to the do loop. Okay, and that's it. This is how we translate the function bubble sort. Any question about this? So the way that it is written as a nested loop. The outer one is a do while loop. The inner loop is a for loop. And notice that how we write. So we write the instructions. Okay, so we have implemented the inner for loop. We have implemented the branch inside the inner for loop. And notice that the last two branches here, branch not equal is used for the for, branch not equal to 0. These two branches are actually going to terminate the for and the outer do while loop. Any question about
Dr.
Yeah,
I've noticed that we didn't use V0 anywhere in this code or the previous one. When do we need to use V0?
Okay, does this bubble sort return any value in V0?
Void, it does not return anything.
Exactly. So what does it do, this function bubble sort?
It will only swap the array.
It's going to modify the array in memory. It's going to modify the array in memory, right?
Yes.
So this function bubble sort, all what it does is going to change the elements inside the array in memory. So therefore, it's going to sort the array in place in memory. It's not going to allocate a new array. It's not going to return anything. It's going just to sort the array in memory in place. So therefore, all the changes will happen inside the array. Now, since we have the address of the array, we can access all the elements of the array. We can read them. This is why I have these two load word instructions. Okay, and we can modify them, we can swap them because we have these two store word instructions. So the load word are going to read the elements of the array. The store, which are here, these are going to write, okay, and swap the elements of the two elements inside the array. So by swapping, we are sorting.
Yeah. What about the previous one, the first one?
So for this reason, we don't really need to return any value in V0 because the bubble sort does not return anything in V0. Okay, you can see that what appears to the left of bubble sort is void. Okay?
Yeah.
So it all depends on the function, what the function is doing. Right. Any other question about the function bubble sort? Yes, Ali.
Shouldn't we take the array of integer a and modify it? Because we don't want to return a value. So we take the array a and modify it. Isn't correct?
We are modifying the array a.
But if you go to the
we are modifying it here, right?
Yes.
So if you find that AI is greater than AI plus 1, we swap them so that, okay, we sort them, okay, in memory. So we are sorting them from the smallest to the largest.
Yeah.
So this is why we store. The store instruction is going to modify the array in memory.
But Doctor, we use register T0, which we copied the array A0.
It's the address.
So we are copying the address.
Yes, you cannot copy the array into a register. You can only copy the address.
Okay.
So T0 contains an address only. The array can be huge. You can actually have million elements inside the array. So how can you copy the array into a register? You can only have the address. The address is just a 32-bit number. The address is just a pointer to the array. You understand this?
Yeah, I got it.
So we use the address because the load and the store instructions need memory addresses. Right. How do we write recursive functions in MIPS using the MIPS architecture? Of course, we write the recursive functions in a high-level programming language. Recursion is something which is very important, and we need to understand it. This is an example of a recursive function. So a recursive function is a function that calls itself. That's the meaning of recursive function. So in this example, I would like to calculate the sum of an array of elements. So I really would like to add here, let me use here my highlighter. So this is my function, which is called recursive sum. It has two arguments. We have A is an array of integers, and we have N, which is the number of elements inside the array. And this function is going to return the sum. Okay, so it's going to add all the elements inside this array and return just one number, which is the sum. Now, this function is written recursively. Of course, we can write it with a loop. We can write a loop to do the addition of all the elements inside the array, but I'm writing it here recursively just to illustrate recursion. It's a very simple function. So I'm writing two recursive calls, so the function is calling itself recursively. So if n is equal to 0, if we have 0 elements, we just return 0. There is nothing to add. If n is equal to 1, we return the value of A0. There is only one element in the array. We return the value of this element. Okay. Now, if there are more than one element, so here you notice that the first two if statements, these are needed to terminate recursion. Because without these two if statements, the recursion can go on and on. We'll have infinitely recursive function. So we have to terminate recursion. So this is the need of these two if statements. So when we return, khalas, we're not going to execute the statements after the if. Now, if we don't return, if we have n greater than 1, yani 2 or more elements, then what we need to do is that we need to make two recursive calls. So the first call to the function recursive sum, okay, notice that the call is done inside the function recursive sum. So the function is calling itself. We would like to add the first n/2 elements of the array, starting at the address, which is the address of the first element of the array. So we start here at the address of A0, and the number of elements will be n/2. And then the second call to the function, so this will give me the first call is going to return someone. Someone will be the sum of the first half elements inside the array. And my second call to the function recursive sum, we pass the address of A at n/2. So this will start at in the middle of the array, and the number of elements will be all the remaining elements, n minus n/2. Now we cannot really use n/2 here because n might not be even, might be odd. Okay, for example, if I have n is equal to 9 elements, and the first recursive call, we are going to add the sum of the first 4 elements. So we use integer division. So 9 divided by 2 will be 4. And then when we make the second recursive call, we say 9 minus 4, it will be the remaining 5 elements in the array. So this is why I wrote it as n minus n/2. If n was even, and let us say n is equal to 10 elements, then the first call is going to take the sum of the first 5, and the second recursive sum is going to take the sum of the last 5 elements in the array. So we get sum 1, we get sum 2, okay, from these 2 recursive calls. And then at the end, just before returning back to the caller, we're going to return sum 1 plus sum 2. That's how the function is written. So we did not really use any loop, okay, in this example. We made the call recursively. So the function called itself recursively, and this is an example of a recursive function. Okay, is this clear? So this is how we write a recursive function in a high-level programming language. So most programming languages, in fact, almost all of them, okay, support recursion. Recursion is very useful, okay, in programming. And you can actually have recursion direct or indirect. Yani in this example, recursion was direct because the function was calling itself recursively. You can also have recursion indirect. Yani for example, you can have, let us say, function f calling function g, and function g calling function f recursively. Okay, so you can actually have this kind of a call in which we have f calling g and g calling f indirectly. Or you can actually have g calling function h and h calling f indirectly. Okay, so you can actually have recursion, okay, in this way also. So recursion actually is important in many programming languages, depending of, so it's important in some problems because depending on the nature of the problem that you would like to solve, you will sometimes you prefer to use recursion over writing loops. But theoretical computer scientists, of course, have proven that anything that is written recursively can also be written in a loop. And you can always convert your function to use loop. But I really would like to illustrate here recursion. In the second programming assignment, we have a recursive function, which is a quicksort. Okay, so it is written recursively, and therefore you have to translate it. You have to use it. You have to use. Okay, you have to write it recursively, also using the MIPS instructions. So when you translate it from high level into assembly, you have to make the function to call itself recursively. So the question is, how do we translate this function into assembly language? This is the question. Any idea how to translate this?
I think first we should determine what we should preserve, what we should save in the stack.
Yes.
Yeah.
Exactly. So the most important question here is that this function recursive sum is going to call itself. So therefore, it's going to lose the return address. Okay. Yes, Khalid.
Yes, doctor. I didn't understand why we are calling twice the function.
Because you see, in the first call, we're adding the first n/2 elements in the array, And the second call, we are adding the remaining elements in the array. So basically, I'm dividing the array into two halves. The first half, we add their elements. So this will be sum1. And the second call, we are adding the second half, okay, the remaining elements in the second half of the array. So this will be sum2. And then at the end, I'm going to add sum1 plus sum2. Okay, so we have two recursive calls inside this example. Of course, you can write it differently, but this is just for illustration, okay, of a recursive function in which we have two recursive calls. So sometimes you can actually have multiple recursive calls inside a recursive function. This will be very interesting, okay? To have multiple recursive calls inside the function, that will be more interesting than just having one recursive call. So in many real programs, you might actually have really multiple recursive calls. And as I said, recursion can be more complex than this because it can be indirect, okay? So not in one function, but across multiple functions, okay? So because this function is not a leaf function, it's calling itself, so therefore it has to save the return address. So the question, if I would like to translate something like this, I must use the stack. I must save, okay, certain registers on the stack. So the question, which registers need to be saved on the stack? Okay, so what's the size of my stack frame? I have to, every time we call the function recursive sum, okay, every time we call it, we must, the recursive sum function must allocate a frame for itself to save certain registers. Now, let me show you this, okay? I'm going to skip the translation here and illustrating the recursive calls. Now, the main function, okay, might call the function recursive sum. So the first call is done by the main function. I'm assuming the main function is initiating, okay, the first call to the function recursive sum. So my first call to the recursive sum, suppose that A0 is the address of the array. It's equal to the address here of A0, and A1 is equal to the number 6. By the way, let me just, what I really would like to do is just move this slide up here. Okay, this will be better. Okay, so now this is my first call to the function recursive sum. Okay.
Which is Dr. n equal 12.
So A1 here is the number of elements. I would like to only to add, sorry, A1 will be the number of elements. Yeah, it will be n, as we have seen here. So A0 will be the address. Okay, so A0 here is the address. So we have A0 and A1. These are my arguments. Okay, so A0 is the address of the array A, and A1 will be n, the number of elements. So suppose that now the main function is going to call the function recursive sum. It has to pass the two arguments in A0 and A1. So suppose that my array now is array A. So it has to pass the address of the array A. So this will be the address of the first element of the array at index 0. And it has to pass n. So n in this example is 6. So we only have 6 elements inside this array. Now the function recursive sum is going to make 2 calls, right? There are 2 calls here, 2 recursive calls. This is my first recursive call. This is my second recursive call. So when it makes the first recursive call, it's going to pass the same address of the array, but it's going to cut n by half. So n was 6. So in my first recursive call, it's going to pass the same A0, but it's going to pass a different value of A1. Okay, so A1 is changing now. Now, because it's making this first recursive call, it's going to make a second recursive call, which is not really shown here. Okay, I'm going to come back to it. There are 2 recursive calls. So this is my first recursive call. Okay. Now, once we enter the function recursive sum, the function is going to also to make another recursive call. So we go down deep. So we have a tree of calls. Now, in this recursive call, it's going to pass again the same address of the array in A0, but we cut 3 in half. but 3 divided by 2 is equal to 1.5, but this is integer division. So therefore, we pass only 1. Okay, so we pass 1. Okay, so that's my first recursive call. So since we have reached here the if statement, the if statement says if n is equal to 1, just return the value of a0. So in this recursive call, we just return the value of a0. So this will be sum1. Sum1 will be a0. Now there is a second recursive call inside the function. So once we return back to the caller, now notice that the caller is also recursive sum. It's the same function. So once we return back to the caller, okay, then it's going to make a second recursive call. Now the second recursive call is going to have to change the value of a0. So a0 has a different value, which is the address of a1, and then a1 will be the remaining number of elements. So we had 3 here, so we passed 1 element and then we passed 2 elements. Now, because this n here is greater than 1, it's 2, it has to make 2 recursive calls. So 1 recursive call is second recursive call. Okay. Now, each recursive call will have n is equal to 1. That's the number of elements, but the address is different. So the address here is the address of a1, and the address here is the address of a2. Notice that it has received here the address of a1 and a0, and therefore it will pass the same address in the first recursive call, but it's going to pass a different address in the second recursive call because we have only 2 elements. Now, once we return a1, so a1 is going to be returned, and so the result of the recursive sum is going to be returned in the register v0. So once we return the result in v0, so this will be sum1, this will be sum2, then the parent here, so this is my parent function. These are the children, okay? So the parent is going to add a1 plus a2, sum1 plus sum2, and return it back to its parent. So it's going to return the sum here in a, so which is the sum of a1 plus a2 back to its parent. Now the parent is going to receive sum1 and sum2. So sum1 will be a0, sum2 will be the sum of a1 plus a2. It's going to add the sum1 plus sum2 and return the sum back to its parent. Now once we have reached the initial call to the recursive sum, so this was actually my first call with 3 elements. It has to make a second call with 3 elements, but starting at the address of a3, and the number of elements will be 3. So because we have 3 here, it has to make 2 recursive calls. So we divide 3 by 2, we get 1. So we got here a0, which is the address of a3, and a1 is just equal to 1. So this is going to return back a3 back to the caller. And then we have a second recursive call starting at the address of a4 with 2 elements. So 3 minus 1, we have the remaining 2 elements. Because here a1 is equal to 2, we have to make 2 recursive calls. 2 recursive calls with 2 different addresses. Each one will have half the elements. So this is going to return a4. This is going to return a5 because n is equal to 1. Now this function here, is going to take the sum of sum1 plus sum2 and return the sum here of a4 plus a5 back to its parent. And this instance of the function recursive sum is going to take the sum of these 2 and return the sum back to its caller. And now this instance of, this is the top level recursive sum, is going to receive sum1 and sum2, and then add them up and return back the total sum back to its caller, which is the main function. Is this clear? This is how recursion works. It's a tree of calls. It's a tree of calls. So each call to the function recursive sum is an instance of the function. It will have its own parameters, a0 and a1. It will have its own return address. Okay, so the return address is different. Okay, because here, for example, the top level recursive sum is going to return back to its caller, which is the main function. Whereas, let us say this instance of the recursive sum is going to return back to its caller, which is this instance of the function recursive sum. So the function recursive sum can return back to itself. Okay, it will return back to itself. So let us see how we translate the function recursive sum into assembly language. Do you have any question about this? I just would like to show you the code, how we translate it into assembly. But this is basically a tree of calls. And every time you call the function recursive sum, it will have a different value of A0 and a different value of A1. So you can see that the arguments are changing. So each call to the function recursive sum will have its own copy of these arguments. It will also have a different value of the return address register, because the return address is going to change. Okay, sometimes, okay, so in the top, okay, in the initial call to the function recursive sum, which appears on top of this tree, the return address is in the main function. Whereas in these nested, okay, recursive function calls, the return address is back to the function itself. So we have a different return address. So therefore, we have to save the return address. Okay. So let me show you how we translate this function. Okay, how do we write it in MIPS? So you can always look back at the code, which is, let me just go back again. I'm going to discard all of this. I'm going to go back here, okay, into the example of a recursive function. I'm going to copy this slide and place it here. So now I'm going to focus on the code, and I really would like to translate this code into assembly. So we're going to write a function here, which is called recursive sum. So this is my recursive sum function. So it starts at this label. Okay, so every time I would like to call the function recursive sum, I'm going to use the jump and link instruction to call the function recursive sum. So the first thing I need to do is that I need to allocate a stack frame. Okay, but before that, there are two if statements here. So these two if statements are essential to terminate recursion. I have the case n equal to 0, and I have the case which is n is equal to 1. So let us write these if statements, because these actually are easy. So if n is not equal to 0, so we branch if n. So n here is A1. So if n is not equal to 0, we branch to L1. Because if n equal to 0, there is no need to branch. I'm going to return 0 in V0. So that's my result, and jump here, use the jump register RA to return back to the caller. So that's my first if statement. That's if n is equal to 0. Now notice that if n is different from 0, we branch to L1. We skip these two instructions. But if n is equal to 0, we are going to execute these two instructions. So we are initializing V0 with 0 because we are going to return the result in V0, and we return back to the caller. So this means that we are going to return 0. That's the meaning of return 0. Now, if n is equal to 1, we reach here the label L1. I would like to check if n is not equal to 1. So we branch if n is not equal to 1. Notice that I look at the complement, okay, of the Boolean expression. So it says that if n is equal to 1, so branch if n is not equal to 1. So I would like to branch here to L2. Okay. And what I really would like to do is I would like to return A0. Sorry, I would like to return A0. Yes, I would like to return A0. All what I have is the address of the array. So the address of the array is passed in A0. I don't really have the value. So what I really need to do is I need to load. So this is the importance of load instruction, because we are going to load the value of the array element from memory. So we're going to use the address in A0. Okay, so that's my memory address. And I'm going to load it into V0 because I have to return it in V0 and just here jump register to return back to the caller. Okay, so I'm returning back to the caller using this jump register. Now, if these two if statements are false, and if n is not equal to 0 and if n is not equal to 1, we come here. Okay, so what I need to do now, I need to allocate the stack frame. So the question is, how many bytes do I need? How many registers do I need to save? As a minimum, I have to save RA, the return address. But in this example, I also have to save my arguments. Why? I have to save here the address of the array, and I have to save n. So I have to save 2 more registers, the argument registers. So rather than saving them directly, I'm going to save S0 and S1, because the convention is that S0 and S1, okay, should be preserved across function calls. And here, because we have nested function calls, okay, we can save these 2 registers. So I'm going to save RA, I'm going to save S0, and I'm going to save S1. So I'm going to use these 3 store word instructions. I'm going to save them on the stack. So for this reason, before I save them on the stack, I have to allocate, okay, my stack frame. So I'm going to decrement the stack pointer by 12 by adding -12. So this will be my stack frame now will consist of 12 bytes. So first we allocate a stack frame consisting of 12 bytes, and I save the return address S0 and S1. Now you say that, okay, what is S0 and S1? We don't really care because these are the old values of S0 and S1. We just save them on the stack before we modify them. Now I'm going to use S0 to save the value of A0. So I'm using move here to copy the value of A0 into S0, and another move to copy the value of A1 into S1. So this way I have preserved the value of A0 and A1. First, I have preserved the old value of S0 and S1, and I copied the value of A0 into S0, and I copied the value of A1 into S1. I cannot modify S0 and S1 except after preserving their value on the stack. So this is why I'm saving 3 registers. You could have stored A0 and A1 directly here on the stack. That will be also another possibility. But I prefer to use S0 and S1 because we have 2 recursive calls. Right. Now, the first recursive call, as indicated here, it has to have 2 arguments. It has to have A0 and A1. Now, A0 is the same. Okay, it's the same address of the array, but A1 has changed from n to n over 2. So therefore, I have to divide n by 2. Of course, you can use the divide instruction, but since division by 2 can be done by the shift right logical instruction, why not shift A1 by 1 bit? This will be division by 2. So I'm going to shift A1 by 1 bit. This is division by 2. Shift can do it much faster, okay, than the divide instruction, and place the result again in A1. Notice that A0 did not really change, so there is no need actually to do anything for A0. This is my first recursive call, jump and link recursive sum. So this will take me back to the beginning, but I don't really need to worry about this code anymore because this is just, I'm going to translate it as it is shown here in my code, in my initial code. So this is my first call to the recursive sum. Okay. I still have to return from this call. So when I return from this call, I'm going to come here, okay, to this slide. We are not really done yet. This is, I need to still make a second call to the recursive sum. So this is my second call to the function recursive sum. But before I make the second call, what I need to do is I need to save someone, and then I have to change my arguments A0 and A1 before making my second call to the recursive sum. Okay, this is something which is very important. So how do we save the value of someone? Well, what we need to do is that first of all, okay, so I need to save the value of someone. I can copy it from V0 to S0. This is how I'm going to preserve the value of someone. So this is why I'm using here S0 and S1, because I can preserve, okay, values in them. This is why I initially here in the previous slide, I saved the value of S0 and S1 on the stack. So I did it this way so that to preserve the value of these arguments and also to preserve the value of someone. Now notice that I need to change the value of A0 and A1. In order to calculate here the address of n over 2, I'm going to take n over 2. So first I'm going to divide n by 2. So this is my shift right logical instruction that will divide n by 2. So S1 here is n. Notice that we have saved the value. Okay, notice that here I save the value of n. Okay, that's A1 in S1 because I need it after the recursive call. So I know that the recursive call, any call, is going to preserve the value of S0 and S1. So for this reason, I use S0 and S1, and I save their values on the stack here before modifying them. Okay, so I know every recursive call is going to do exactly the same thing. So I'm going to calculate here n over 2 using the shift right logical. So shift right by 1 bit, this is division by 2, and then multiplied by 4, shift left logical, and place the result in T1. So now we have multiplied the index by 4, and then use an add u instruction to add it to S0. Now S0 is nothing but the address of the array A. Add it to T1, which is the index multiplied by 4, and place the result in A0. This will give me the address of AN divided by 2. So these three instructions here are used for address calculation, to calculate the address of AN over 2. So I need to pass the address in A0. I need to pass n minus n over 2 in A1. So n is in S1, and n over 2, already we have calculated this in T0. So do a subtraction, and this will give you the value of n minus n over 2, and replace the result in A1. So we have the two arguments in A0 and A1. I need to save the result of the first recursive call, sum1. I'm going to save it in S0. Okay? And then I make my second recursive call. Now, once we make the second recursive call, I will have sum2 in V0. I already have saved sum1 in S0. So we add sum1 plus sum2 and replace the result in V0. Now, before returning back to the caller, I have to restore the old value of the return address, the old value of S0 and S1. This is very important. So load word, load word, load word. Okay, so load the return address S0 and S1 using my stack pointer and different displacements here. We follow exactly the same displacement that we used here. Okay, for saving these three registers, I'm using exactly the same displacement for restoring their values. So once we have them, we have these three registers restored, then I can free my stack frame, which is no longer needed. So I can just add 12 to my stack pointer. So this will restore my stack pointer and jump back here to the caller by saying jump register RA. Okay. Now, when you jump register RA, this will take you to where the call was made. Okay, so the call actually can be made in three different places. It can be made, okay, in the main function. So if the call was initially made in the main function, you return back to the main function. Okay, the call can be made here. Okay, let me just use my pen tool. If the call was made here, okay, for my recursive call, then when we return here. If the call was made here, then when we return here. So therefore, from this jump register, if you are returning from a recursive call, you can return back here, or you can return back here. Okay, so you can return from your first recursive call, or you can return from your second recursive call, depending on the value of this RA. So this is why for every recursive call, we save the return address.